So I do have a fan running. It's really, really hot in my house right now. I hope the fan is not messing up with the audio of this video. I don't know. We'll see. Anyway, for topic three, we need to talk about using a calculator to evaluate inverse secant, cosecant, and cotangent. And so the issue with this is that we don't have an inverse secant, cosecant, or cotangent button on our calculator. We don't have a secant, cosecant, cotangent button on our calculator. So this is problematic. We have to find a creative way around this. Okay. So let's first talk about cosine and secant. So cosine inverse and secant inverse, really. So we have to go back to what we learned in goodness, like 7.3, 7.4, something like that. Back then, we learned that if we have a point, we'll call it xy, on the terminal side of an angle theta, we have the following ratios. So for cosine, we would have that cosine of whatever this angle theta was would be the ratio x over r, and secant of theta would be the ratio r over x. And that should kind of make sense because secant and cosecant are reciprocals of each other, so those ratios should be reciprocals of each other too. So let's think about what this angle is. So we're going to draw an angle in standard position, meaning the vertex is at the origin, the initial side is on the positive x-axis, and then we sweep open in some way, shape, or form, okay? And then we're going to say, hey, we have this point on the terminal side of this angle theta that's called xy, okay? So theta's right here. Well, using that point, we could drop it down to the x-axis, and we could create essentially this right triangle. And this distance from the origin to the along, we'll say the x-axis is just some x value. And then the distance between the terminal side and the initial side is some distance along the y-axis, essentially. And then we would say the distance from the origin to the point on the terminal side was r. Okay, so that's kind of how we labeled our angle theta. Okay, and we know that there's a relationship between theta and cosine. For example, cosine of theta relates the side adjacent to the angle theta and the hypotenuse. So that's where we get this ratio x over r. And then we also know that secant is the reciprocal of cosine. So then secant of theta is just going to be the reciprocal to that ratio, or r over x. Okay, so what does that mean in terms of these inverse trig functions? Well, using this given information, the picture that we've drawn, and these ratios for cosine and secant, we could then say that inverse cosine is going to equal some angle theta, this angle theta that we just drew, okay? And the input value is going to be that ratio. So we would say this ratio right here. So we would say that inverse cosine of the ratio x over r is going to equal this angle theta. Well, similarly, if we take secant inverse or inverse secant of its ratio r over x, we get the output that is that same angle theta. So even though we have these two different ratios, because they're applied to the same angle theta, we have a workaround for this calculator issue. So this is the same theta for both of these, okay? So again, inverse cosine of x over r is going to equal theta, and inverse secant of r over x is going to equal the same theta. And this works because when we were first building these trig functions, we acknowledged the fact that trig functions are not one-to-one. So we basically restricted the domain of all of the different trig functions in such a way that we had a segment of the trig function that was one-to-one. And then by doing that, when we built those inverse trig functions, we created a situation where we have a restricted range. So we're limited to what these inverse trig functions can spit out for the angle theta. But the good news is cosine inverse or inverse cosine and inverse secant, we have basically the same range restriction. We have like one little extra thing for inverse secant, but otherwise we've restricted them in the same way. And that's really, really great news for us because, as I have written out here, since the range restriction on theta is basically the same for inverse cosine and inverse secant, we can use the inverse cosine function on the calculator to find inverse secant. Okay, and that's really, really helpful because keep in mind, even though we have different ratios here, they were spitting out the same angle theta. And they're spitting out the same angle theta because we've restricted them in the same way. Okay, now let's do the same thing, but let's talk about sine and cosecant. Okay, so again, given a point xy on the terminal side of an angle theta, consider the following. we have that when we have some angle theta, that sine is going to be the ratio y over r, and cosecant is going to be the reciprocal of that. It's going to be the ratio r over y. So again, let's draw this. So again, imagine we have some angle theta. It's going to be in standard position, meaning the vertex is at the origin, the initial side is on the positive x-axis, and then we sweep over, open. So we have some generic angle theta, okay? Well, when we have some point on the terminal side, we can sort of use that to create this right triangle, where we have some distance along the x-axis called x, and then some distance along the y-axis called y, and then we always say that the distance from the origin to that point on the terminal side, we got in the habit of calling it r. Okay, and we know the relationship between sine and theta is that sine of theta is the opposite side over the hypotenuse. So the opposite side compared to this angle theta would be y, and the hypotenuse would be r. So that's where this ratio y over r came from. And then because we know that cosecant is the reciprocal to sine, its ratio would be r over y. So using that information, the picture we've drawn of theta and these ratios, we can then say, well, inverse sine of the ratio y over r is going to equal theta, and then inverse cosecant of the ratio y over r is going to equal the exact same theta, okay? So this is the same theta. And remember, when we're talking about these inverse trig functions, the inverse trig functions operate on a ratio and then they spit out an angle. Spit out is a horrible way to say the output value is an angle, but the output value is an angle. While it's a restricted range, it's still an angle that we get out. And so the great news here is that when we were building inverse sine and inverse cosecant, we restricted the domain of sine and cosecant the same way, which means the restricted range is basically the same for both of these functions. So what we have written out here is that since the range restriction on theta is basically the same for inverse sine and inverse cosecant, we can use the inverse sine function on the calculator to find inverse cosecant. And that's really cool because again, we have these two different ratios, but they're essentially applied to the same angle, okay? And since we restricted our range the same way for inverse sine and inverse cosecant, we can use the inverse sine function on the calculator in a kind of creative way, but we can use it to get the inverse cosecant. Now, just like with just basically defining these inverse trig functions, it's cotangent that's weird, okay? So I'm not going to go too deep in this, just know cotangent is the weird one. Now, the issue with cotangent, when we were building the inverse tangent and the inverse cotangent functions, we of course had to restrict the domain on the standard tangent, standard cotangent functions, but we couldn't restrict those domains in the same way. And because we didn't restrict the domains in the same way, that means the range restriction is not the same for inverse tangent and inverse cotangent. And that's a problem. So that means we can't use the inverse tangent button on our calculator to help us find the inverse cotangent. But what we did realize while we were building the inverse cotangent function is that its range is restricted in a very similar way to inverse cosine, okay? So because of that, I'm going to say because inverse cotangent has a range restriction similar to inverse, well, let me just write inverse cosine symbolically. To inverse cosine, we will use inverse cosine on the calculator to help us find inverse cotangent. Okay, and I know that's really weird for us, but remember, it's all about how we restricted the range, and the range is restricted based on how we initially restricted the domain of the standard trig function so that we can build these inverse trig functions, okay? So let's go ahead and come down here and look at some examples. So these are a little bit weird. The good news is I was chatting with a buddy of mine who teaches Calc 1, and then I was talking to somebody who tutors a lot. And this is not something that's going to come up a ton for you, okay? So don't get too bent out of shape. It's weird. It's not impossible. It's not even necessarily hard. It's just weird, okay? And sometimes we get all bent out of shape about weird stuff. All right, so the directions for example 3 say use a calculator to approximate each expression in radians. So keep in mind we need to be in radians, rounded to 2 decimal places. And the first thing we have is inverse secant of 5. Okay, well keep in mind when we're talking about inverse secant operates on a ratio, meaning the input value is a ratio. The output value would be some angle theta, okay? Now, we need to keep in mind the domain and range. So when we're talking about the domain of inverse secant, it is the situation where we have the absolute value of x needs to be greater than or equal to 1. Well, 5 is our value for x. Is that greater than or equal to 1? Absolutely. So we're good here. The range you have to remember is, so when we're dealing with secant, that's similar to cosine, because remember, secant and cosine are reciprocals of each other. And luckily, when we built inverse cosine and inverse secant, we could restrict them the same way. So we have the situation negative, not negative, I was about to do cosecant. We have 0 to pi. We just have to be really careful and make sure theta is not equal to exactly pi over 2 because we have an issue there. Okay, so that's all well and good, but what in the heck do we do? We have to start thinking of ways to get equivalent statements. We know that we can use inverse cosine on the calculator to help us find an inverse secant, but we got to do some tricky work here. Okay, one thing I need you to understand is that secant inverse is not equal to 1 over cosine inverse or inverse cosine. So we can't just do that. We have to be a little bit more careful. So initially what we're going to do, and you can kind of, I'm going to show you all the steps here, and then we can sort of take some liberties and sort of skip to the chase with other examples. But for this one, let's build it from start to finish. So I want to basically liberate the 5 from the argument, because if I could rewrite this as an equivalent statement where I have secant of theta equals a ratio, then we have something that we can kind of work with, because secant is the reciprocal of regular cosine. Okay, so I'm going to start by taking basically just regular secant of both sides of this right here. So we get secant of inverse secant of 5 is going to be secant of theta. Well, the good news is because we double checked the domain and 5 is definitely part of the domain of inverse secant, we can just say that secant and inverse secant, they just undo each other. Remember, we talked about that in 8 point. Well, I guess earlier in this section, I can't, but basically what we know is if you take the inverse of a function and you compose it with the actual function, they undo each other as long as you're okay with the domain. So we're going to say secant of inverse secant. They'll just unravel each other, leaving us with just 5. And then on the right-hand side, that leaves us with secant of theta. So I'm going to write it kind of in a better order. So we have secant of theta is now 5, and we like this. So now we have a situation where we have regular secant of some angle is going to have a ratio of 5. And because we're dealing with regular secant, we can now relate the fact that regular secant and regular cosine are ratios of one another. Okay, not ratios, reciprocals of one another. It's really late. Okay, so I could rewrite this and I could say, okay, this is going to be the same thing as cosine of theta, but it's not going to equal 5. It's going to equal the reciprocal of 5, which is 1/5. So far, we've just been rewriting. We've been finding equivalent statements. These two things are going to be the same. They're going to have the same angle theta, okay? But this still doesn't help us because we need to find some way to find the inverse secant of 5. So let's take the inverse cosine of both of the sides of this. So we're going to take inverse cosine of cosine of theta and inverse cosine of 1/5. Well, as long as theta is something in our domain, inverse cosine and cosine, they just unravel each other. So that leaves me with theta equals inverse cosine of 1/5. And finally, this is something we can do on the calculator. All right, because remember, when we're dealing with an inverse trig function, we operate on a ratio and it spits out an angle. We needed to find a way to get the angle. Okay, so we need to find some way that we could get the angle where we have secant inverse or inverse secant of 5 equals whatever this angle is. So let's go to the calculator. This was a very long, drawn out explanation. The others are going to go much, well, I don't want to say much quicker, but they're going to go quicker. Okay. All right. So we can now do inverse cosine. So we go secant cosine. And remember, we have to apply inverse cosine to 1/5, not 5. So 1 divided by 5. We were told to write our answer in radians. You can see up here, I'm definitely in radians. Make sure you are too. And then we're going to round to 2 decimal places. So we get 1.369, which is going to round to 1.37. Okay. So that was a lot of like words a moment ago, but we can essentially say that theta equals 1.37. Okay. So it's tricky, but that is the full, long, drawn out process. Now, you can kind of jump to the chase and you can sort of jump from, here to here and then from here to here pretty quickly just by understanding that we're not applying inverse cosine to the same ratio. But there you have it. Okay. Part B, we have inverse secant of 0.8. And the first thing we need to acknowledge or address is this input value in the right domain? Okay. So remember, the domain for inverse secant is that the absolute value of x has to be greater than or equal to 1. Well, this right here is essentially our x, and we have 0.8. So 0.8 is not in the domain of secant inverse or inverse secant. Okay, so right off the bat, we can just say, hey, this is not defined. There's nothing we can do about it. We're done at this point. But let's say that you didn't play around with your domain and you didn't catch that 0.8 was not in the domain of inverse secant. So instead, we'd say, okay, we had secant or inverse secant of 0.8, and we know that has to equal a theta. Okay, we can't really I don't want to say you can skip these steps. You can kind of skip these steps, but know what steps you're skipping. We can kind of cut to the chase and say, okay, theta has to equal inverse cosine of the reciprocal of whatever your input was for inverse secant. So the reciprocal of that, we're just going to say is 1 over 0.8. And then we can try this on our calculator. Okay, so when we go to the calculator for this one, we already know because we checked the domain of inverse secant and 0.8 is not in the domain, but let's go ahead and do this on the calculator so you know what you would see if you didn't catch the domain restriction initially. So we would go secant cosine, and then we want to apply this to 1 over 0.8. And we get this. So we get that error and it says, hey, we have an issue with the domain here. Okay. So you can save yourself a little bit of heartache if you really understand the domain and range and how these work. The domain of secant of inverse secant is the input has to be, the absolute value of the input has to be greater than or equal to 1. We were outside of our domain right off the bat. If you didn't catch that and you did this work, you would still get that this is not defined. We are outside of our domain. Okay. And then finally, we get to the one that we have all been holding our breath for. We're going to look at an inverse cotan function. Okay. So we have cotangent or inverse cotangent of negative 2 over 3. So let's think about this for a moment. Okay. So we can't just do some fancy rewriting. The issue is that cotangent, inverse cotangent and inverse tangent, they don't have the same range restrictions. So we can't use that. We can't like rewrite inverse cotangent as some tangent function like we did over here for part A with secant and cosine, okay? And what we do know is that when we're talking about inverse cotangent, it does have the same range restriction as inverse cosine, but we can't just rewrite this as a cosine because cosine and cotangent aren't reciprocals of each other. And that's what we were allowed to do over here in part A. We were allowed to kind of rewrite things because we knew there was this relationship with secant and cosine. They are reciprocals of each other. And we also know that inverse secant and inverse cosine have the same range restriction. Well, we're backed up against a wall over here. We know that we have the same range restriction as inverse cosine, but cotangent and cosine aren't reciprocals. So what in the tarnation do we do? Well, here's what we do. We acknowledge that when we're dealing with inverse cotangent, it operates on a ratio and it has an output that is an angle theta. So we know this is eventually going to give us some angle theta. That's what we're looking for. What angle theta has a cotangent ratio of negative 2/3? Okay. So let's see if we can rewrite this and come up with an equivalent statement, but written in terms of just cotangent. Okay. Now this is kind of trippy. We know this is our input. We know this is our output. And essentially what we could do is we could say, okay, if we take cotangent and apply it to theta, just regular cotangent, cotangent operates on an angle, so we could say cotan of theta is going to have some output that is a ratio. So we can rewrite it kind of like we did from here to here. We're just skipping the side work, okay? We're just saying, hey, we understand that's how this works, so we can rewrite this, okay? So instead of inverse cotan of a ratio equaling an angle, we're going to have cotan of some angle equaling that same ratio, okay? But then what? We can't suddenly rewrite this as a cosine because cosine and cotangent are not reciprocals of each other. Instead, we draw a triangle, okay? So let's think about a couple of things. First of all, when we're dealing with inverse cotangent, we know that our range restriction is from 0 to pi, okay? So thinking about cotangent, where are the ratios for cotangent? Negative, because our input here is some negative ratio. Well, cotangent is positive in quadrant 1 and it is negative in quadrant 2. So I need to build a triangle. So I need to basically draw some angle that would end up having this ratio of -2/3 for cotangent. And this angle slash triangle need to live in quadrant 2. Okay, so let's draw that. I said 2, really funny. I did not mean to be that sassy, but it's late and I get sassy at night, I guess. Okay, so we're going to draw some angle theta, okay? So we're going to draw some angle theta. It has to live in quadrant 2, okay? And that's going to create some right triangle. We call these reference triangles, okay? So we're going to build, the angle we're going to look at is right here. Now we know the ratio for cotangent of this angle has to be -2/3. So let's think about what cotangent is. As far as ratios go, cotangent has to be the reciprocal of tangent, okay? Tangent we know is opposite over adjacent. So that means cotangent is adjacent over opposite. And we know that cotangent is also -2/3. So the side adjacent to theta needs to have a length of -2, and the side opposite of theta needs to have a length of 3. We then have to find the hypotenuse here, okay? So we just use the Pythagorean theorem. So we're going to call this C for now. So C squared equals A squared plus B squared. So C squared is equal to 4 plus 9. So C squared is 13, which tells me C is square root 13. So the hypotenuse of this triangle that we just created is square root 13, okay? Now here's the deal. We need to relate cotangent or inverse cotangent to inverse cosine, okay? Because remember, those two have the same range restriction. So essentially what I need to do is look to figure out what cosine of theta would end up being. So this theta that we've drawn up here in this picture, what would the cosine ratio be? Well, cosine is adjacent over hypotenuse. So we would say it's -2/√13. And this is like the one time that I'm going to be like, don't waste your time rationalizing this one because we're essentially just going to plug this into a calculator. Okay, so this is well and good. We now have a cosine relationship. But we need an inverse cosine relationship. So remember, inverse cosine operates on a ratio and gives us an output that is an angle. So we could say, okay, inverse cosine of -2/√13 is going to equal this very same theta that we have drawn here that relates our cotangent. And this we can put in our calculator, okay? So it's a lot of work and it's wacky and it's weird. And thank God it's not something you're going to do a whole lot of, okay? So this isn't something that you need to like lose sleep over, but you do need to understand it for the sake of this course, okay? So let's jump over to our calculator, what feels like 45 minutes later. So let's jump over to the calculator and we're going to do, okay, we're going to clear that and we're going to go inverse cosine, okay, because remember cosine, inverse cosine, and inverse cotangent have basically the same range restrictions, so they'll spit out the same angle. And we wanted to look at the ratio -2 divided by square root 13, okay, and make sure you're in radians, which I am, I know I am, but make sure you are. And then we're going to round this 2 decimal places. So we get 2.158, so let's round this to 2.16, okay? So the angle theta in radians would be 2.16. So I know this video is really long. I don't want to rush, especially with these things that are kind of weird. I really want to explain them. Okay, so apologies for this being long, but I think in the end it's worthwhile. Okay, so there you have it. That is how you can use a calculator to approximate inverse secant, inverse cosecant, and inverse cotan. A little weird, all right, but you got this.